Welcome to Cyber Mornings Daily. For today's deep dive, I want you to imagine designing a bank vault.
Okay, a bank vault.
Right. You've got these 3-foot solid steel doors, biometric retinal scanners, an interlocking laser grid, and then you realize the architect accidentally left the master blueprints just sitting on a table at the public library.
Oh, man. Yeah, that is a great way to put it.
Because that is exactly what is happening in the world of software development right now. I mean, we build these incredibly sophisticated digital fortresses, but the foundation they sit on, like the invisible infrastructure that you and I rely on every single day, is just riddled with structural flaws.
It really is. It's actually a terrifying reality when you look beneath the surface. So today we're analyzing 3 critical cybersecurity stories that reveal exactly where those hidden vulnerabilities lie.
Yeah, we're basically looking at the city's plumbing. You never think about the pipes underground until a main breaks. And today we're looking at 3 massive invisible leaks.
Exactly. So if you're a developer managing dependencies, or an IT professional running servers, or honestly just someone who uses an Android phone or trusts the smart devices in your house, this deep dive is going to show you just how fragile our digital ecosystem truly is.
Yeah, because we have a fantastic stack of recent security write-ups today. We are pulling from independent researchers, AI security firms, and cybersecurity companies like RunZero and JFrog.
And we are covering a lot of ground. We've got a deep Linux kernel flaw, a bug in an embedded file system that is almost certainly sitting inside a device in your house right now, and a highly targeted state-sponsored supply chain attack.
Right. And what makes today's stack so compelling is the contrast in how these flaws are actually being found.
Yeah, it's fascinating because in our first story, we'll see how human ingenuity is still absolutely critical at the bleeding edge of complexity.
Right.
But then in the second, we'll look at how artificial intelligence is completely flipping the script, succeeding where human auditors failed for literally years.
And then finally, we'll look at what happens when threat actors bypass the code entirely and just go straight for the developers.
Right, the human element.
So, okay, let's unpack this first story because it sounds like something straight out of a thriller. There is this newly disclosed Linux kernel flaw. It's called bad epoll.
Bad Apple, yeah.
The official designation is CVE 2026-46242. And an independent researcher named Jae-Young Chung discovered it.
Incredible work by him, honestly.
Seriously. And from what I'm reading, this bug essentially allows an ordinary user like someone with 0 special privileges to gain full root control of a machine.
Total system takeover.
Yeah.
Yeah.
And it affects Linux desktops, servers, and critically Android devices. But before we get into the actual exploit, what exactly is epoll? I mean, I know it acts as some sort of traffic cop for data, but how does it work under the hood?
Right, so to understand epoll, you kind of have to look at how operating systems handle network connections. Imagine a high-traffic web server. It might have tens of thousands of open network connections or files at any given moment. The server needs to know when data arrives on any of those connections so it can actually process it.
That makes sense.
But in the old days, the system had to constantly ask every single connection, do you have data? Do you have data? Which is just incredibly inefficient.
Right, just wasting CPU cycle.
Exactly. So epoll is a standard feature in Linux that solves this. It basically allows a program to register all those connections and then just go to sleep. Epoll taps the program on the shoulder the very instant a specific connection is ready to be read or written to.
Okay, so it's basically a highly efficient notification system. Servers, web browsers, network services, they all lean heavily on it to function at scale.
They absolutely do. You cannot just turn it off or disable it to protect yourself. I mean, it is a load-bearing pillar of the Linux operating system.
Okay, so how does a standard user leverage a notification system to get root access? Because the sources say the technical breakdown of bad epoll is that it's they call it a use after free race condition.
Yes.
Can you walk me through the mechanics of that?
Absolutely. So a use after free bug happens when memory management just goes wrong. The kernel, the core of the operating system creates an internal object in its memory to keep track of this specific epoll task.
Right.
When the task is done, the kernel says, okay, I'm finished with this object, free up this block of memory so something else can use it.
So it empties it out.
Exactly. But in a use after free scenario, another part of the system somehow still holds a reference to that exact memory address. And it tries to actively write data into it after it's already been freed and reassigned to something else.
Oh, wow. So it's like the front desk at a hotel checking out a guest.
Sure.
Right. And they hand the room key to a completely new guest, but the cleaning staff is still inside, emptying the trash and rearranging the furniture.
That is a phenomenal analogy, yes.
So for a split second, there are conflicting instructions on who actually controls the room, and in that split second, an attacker slips through the door.
Precisely. Because if an attacker can predict or control what the kernel puts into that hotel room after it's been freed, they can overwrite critical security structures.
Oh, so they just changed the locks.
Right. Once
Right.
they corrupt that specific kernel memory, they can rewrite their own permissions. They escalate their access from a restricted user account all the way up to root, which is the highest level of system control.
That's terrifying. But reading through Chung's write-up, the timing required to actually pull this off seems almost impossible.
It is incredibly difficult.
Yeah, because the window where these two paths actually collide, the race condition itself, is microscopic.
Yeah.
He said it's only about 6 machine instructions wide.
Yeah, basically invisible.
So a random, accidental attempt to trigger this would almost never land in that exact window. How is this actually exploitable in the real world?
Well, that's where Chung's human ingenuity really comes in. Like you said, a 6-instruction window is roughly a fraction of a millisecond. You can't just guess that timing.
Right.
But Chung managed to build an exploit that artificially widens that window. He created a highly specific setup that forces the kernel to pause or slow down exactly when those instructions are executing.
Wow. So he's stretching out that millisecond.
Exactly. He gets the system to retry the race condition over and over again without crashing the entire machine. By carefully manipulating the system's scheduling, he successfully reaches root about 99% of the time on the systems he tested.
99% of the time. That is insane. And what's wild is the environment where this can actually be triggered. The documentation notes that this attack can be launched from inside Chrome's renderer sandbox.
Yep.
Now, the sandbox is specifically designed to isolate web pages, right? It's supposed to block almost every single kernel bug from reaching the core system if you, like, click a bad link. But bad ITPOL punches right through that isolation.
It punches right through. And furthermore, it reaches Android, which is rare because most Linux privilege escalation bugs actually fail to do that. Android has a highly customized lockdown environment.
Okay, so if you're an IT admin or, just holding an Android phone right now, here's the practical context. If your device is running on an older 6.1 based kernel like the Pixel 8, for example, you are unaffected.
Right. You're safe for now.
Yeah, this specific bug didn't arrive until kernel version 6.4. But for the affected systems, you'll need to apply the upstream commit.
Which means the source code has been patched directly by the Linux maintainers.
Right, but you might have to wait for your specific operating system distribution, like Ubuntu or Debian, to release their own automated update, which is known as a backport.
Exactly. And just to reassure everyone, there is no sign of this being used in active attacks yet. But the proof of concept is out there, meaning the clock is absolutely ticking for defenders.
But wait, we need to talk about the AI angle here, because I genuinely don't understand this part of the story.
Well, this is the most fascinating part.
Right. Both this bug and another sibling bug trace back to a single change made to the EPOL code in 2023. Anthropic's most powerful AI model, Mythos, recently analyzed this exact stretch of source code.
And it found the first bug.
Yeah, it successfully found the first bug, which was patched earlier in the year, but the AI completely missed bad EPOL, which was sitting right next to it.
Just completely blind to it.
So if an AI as smart as Mythos can spot one flaw, why is it completely blind to another one right next to it? I mean, is it like looking for a needle in a haystack, except the needle only exists for a fraction of a millisecond? Isn't code analysis what AI is supposed to be best at?
You would think so, right. But race conditions are really the Achilles heel of current AI analysis.
Yeah.
Chung offered 2 compelling reasons why the AI likely missed it.
Okay, what were they?
First, because that timing window is so incredibly tiny, the exact sequence of concurrent events is just immensely hard to conceptualize. AI models are great at looking at linear logic. If A happens, then B happens.
Right, straight lines.
Exactly. But a race condition requires visualizing 2 separate threads of logic executing simultaneously and finding the exact millisecond they incorrectly intersect. Even for an advanced AI staring directly at the code, it's a massive conceptual blind spot.
So it's like trying to predict a 6-car pileup by just looking at a static map of the highway. You know the roads intersect, but without seeing the speed and timing of the cars, you just can't predict the crash.
That is a perfect way to look at it. And the second reason is the lack of runtime evidence. Normally, the Linux kernel has a built-in memory bug detector called Kasan.
Kasan.
Yes. It acts like an alarm system for bad memory access. But once the first sibling bug was patched, bad EPOL's specific memory error usually didn't trip Kasan. The alarm just never went off.
Oh, wow.
So an AI agent testing the code dynamically wouldn't see any flag indicating something was wrong. It leaves no trace.
This proves that, at least for now, humans are still required for the hardest edge cases. You know, the bug the AI walks right past is the one the human researcher has to catch.
Exactly. We aren't obsolete just yet.
Which is a fascinating dynamic. I mean, we've talked about AI missing these accidental blind spots in our code, but what happens when the code is so ubiquitous and the human reviewers are so fatigued that the exact opposite happens?
A total role reversal.
Right. And that brings us to our second story. We're looking at a set of older, widespread bugs where AI succeeded wildly, uncovering massive flaws that human auditors missed entirely. We are talking about FATFs.
Yes. So the security firm Run Zero just disclosed 7 vulnerabilities in FATFs.
Yeah.
And for context, this is a very small, highly efficient file system library. It allows embedded devices to read and write FAT and XFAT formats.
And it is literally everywhere. I'm talking security cameras, drones, industrial controllers, hardware crypto wallets, ATMs.
Voting machines, too.
Yeah, voting machines. It is baked into the firmware of millions of embedded devices. And Run Zero found that all 7 of these bugs work the same basic way. The device tries to read a storage volume like a booby-trapped USB or SD card that has been deliberately malformed, and FATF just mishandles that bad data.
And the worst of the bunch is CVE 2026-6682. This is an integer overflow in the code that mounts a FAT32 volume.
Okay, let's break that down for a second. How does an integer overflow actually lead to a system compromise?
Well, think of an integer overflow like the mechanical odometer on an old car.
Okay.
If it hits 999,999 miles and you drive 1 more mile, it doesn't go to 1,000,000. It rolls over to all zeros.
Right, resets.
Exactly. So in software, if a program calculates the size of a file and a malicious actor feeds it a number so large that the calculation rolls over, the system suddenly believes a massive file is actually tiny.
Oh, I see where this is going.
Yeah, it allocates a tiny piece of memory for it.
Yeah.
But then the attacker forces the system to copy the massive file into that tiny space. The data overflows its boundaries, corrupting the adjacent memory.
And because we are talking about embedded devices, the impact is devastating. I mean, modern desktops and smartphones have advanced memory protections, things like address space, layout randomization, or stacked canaries that make memory corruption really hard to exploit.
Right, they have safety nets.
But a security camera or an ATM usually lacks those protections, which means any physical access leads to a total jailbreak. You walk up to a public kiosk with a modified storage card, plug it in, and you instantly have full control of the system.
It's a worst-case scenario for physical security. But the patching nightmare here is arguably worse than the bugs themselves.
Why is that?
Because FATF is maintained by one single developer in a small corner of the internet.
Right.
Run Zero tried repeatedly to contact them. They even looped in Japan's JP-CERT Coordination Center.
Yeah.
Zero response. Nothing.
Wow. So there is no official upstream fix for these memory corruption bugs. There's no security mailing list to warn everyone. The burden falls entirely on the downstream vendors, massive companies like Samsung or platforms like MicroPython and Zephyr, to realize they are vulnerable and fix the code themselves.
Exactly. And historically, downstream fixes for embedded firmware can take years to roll out to consumer devices.
That's if they ever get patched at all. Many of these devices are essentially abandoned by their manufacturers the day they ship.
Unfortunately, yes.
But we have to talk about how these bigs were found, because this is where the AI contrast from our first story is so stark. I remember reading about manual code audits back in the day. You'd have security researchers staring at thousands of lines of C code until their eyes blurred, hunting for bad logic.
It was exhausting work.
Yeah, and in fact, back in 2017, Run Zero manually audited this exact FATF's code by hand and found almost nothing worth reporting.
That's right. They missed it entirely. But fast forward to 2026, and their methodology changed completely. They used a totally off-the-shelf AI setup.
Just standard tools.
Yep. Visual Studio Code paired with GitHub Copilot, set to auto mode, and just a few simple text prompts.
And what did the AI actually do with those prompts?
The AI easily built a fuzzer. Fuzzing is a technique where you throw massive amounts of malformed, randomized garbage data at a piece of software at incredible speeds just to see where it breaks or crashes. Writing a good fuzzer for a specific library usually takes a lot of time and deep domain knowledge. But this basic consumer-grade AI setup analyzed the FATF's code, understood how it ingested data, and automatically wrote the testing harness.
Just like that.
Just like that. It then unleashed that garbage data and easily surfaced all 7 zero-day vulnerabilities that human auditors had walked right past a decade earlier.
Which brings up a really thorny question. Run Zero published all of their exploit material, the proof of concept images, the AI prompts, the test, harness all of it.
They did.
So what does this all mean for us? If a standard $20 a month AI pipeline can find 0 days this easily in ubiquitous software, aren't we basically handing a loaded weapon to anyone with a chatbot subscription? Why publish the exploit material at all if there's no official patch?
Well, if we connect this to the bigger picture, you have to look at the reality of the current threat landscape. Run Zero's point is blunt, but it's accurate. If cheap, off-the-shelf AI can find this in an afternoon, well-funded malicious actors are already doing it at scale.
So the bad guys already have this capability.
Absolutely. Sitting on these bugs quietly and practicing security through obscurity protects absolutely no one. It just leaves the defenders blind while the attackers have a field day.
So the barrier to entry for vulnerability discovery has just completely evaporated.
Exactly. And this isn't an isolated incident. Just recently, Google's AI agent, Big Sleep, found a highly exploitable memory bug in Squalite, which is one of the most widely used database engines in the world.
Oh, wow, yeah.
And another autonomous agent recently found 21 memory safety bugs in FFmpeg, a video library used by almost everyone. AI is drastically lowering the cost of discovery. We have to assume the attackers already know about these flaws, which means defenders need the technical details immediately so they can build detections and write their own patches.
Wow. Okay, so we've talked about AI missing bugs, and we've talked about AI finding massive flaws, but AI fuzzer tools are completely useless if the code is actually doing exactly what it was programmed to do. What happens when the developer themselves is tricked into writing the malware? Here's where it gets really interesting. That brings us to our third story. A highly targeted, state-sponsored supply chain attack.
This is a massive shift in tactics. We're moving from exploiting the code to exploiting the people writing the code.
Yeah.
Threat actors linked to North Korea have launched a sophisticated campaign on NPM. Now, for context, NPM is a massive online registry where JavaScript developers download pre-written code packages to use in their own projects. It saves them from reinventing the wheel every time they build an app.
Right. And what the attackers did was upload malicious packages that completely mimic legitimate development tools. Specifically, they targeted something called roll-up polyfill tools.
Very widely used.
Yeah. So if you're an engineer listening to this, think about your Friday afternoon routine. You're moving fast. You're trying to finish a build. You might mean to type the command to download the real tool, which is roll-up plugin polyfill node. But you make a tiny typo, or you copy-paste the wrong link, and you accidentally download the North Korean spoof, which is called Rollup Packages Polyfill Core.
And the disguise is flawless. The description, the metadata, the naming space, it looks perfectly identical to the real thing. Developers place a huge amount of blind trust in package managers, and the attackers are weaponizing that fatigue.
But once that fake package is downloaded, what actually happens? Because the sources say this isn't just a simple virus, it is an incredibly sophisticated multi-stage infection.
It is deeply layered. Hidden inside the lookalike package is a base64 encoded command.
Let me stop you there. What is base64 and why use it? I mean, is it some kind of encryption?
No, it's not encryption at all. It's a translation mechanism. Base64 takes standard text or binary data and translates it into an alphabet of 64 standard characters.
Okay, but why go through the trouble?
Attackers use it because many simple security scanners only look for plain text malicious commands. By translating the command into a block of random-looking base64 characters, it slips right past basic text scanners.
Ah, I see. So the hidden command executes, and then what?
That command silently reaches out to the internet and installs a second-stage payload. But to avoid suspicion, this payload is disguised as a harmless SVG image sanitizer with these really mundane names like React Icon SVGs or Quirky Token.
Why an SVG sanitizer specifically? That seems so random.
Well, because SVG files, which are scalable vector graphics, are actually just large blocks of XML code. Developers expect image sanitization libraries to process massive, messy blocks of code.
Oh, that's smart.
Yeah, so when the security software sees this library processing dense, complex logic, it looks completely native and normal. It's the perfect camouflage.
That is incredibly devious. So the trap is set. What does the payload actually do once it's running?
Those fake SVG utilities fetch a JSON object from a service called JSON Keeper. They run checks to ensure they aren't being analyzed by researchers in a cloud sandbox, and then they finally decrypt a hidden JavaScript payload.
And what's in the payload?
This payload grants the attackers full, interactive remote access to the developer's machine.
We're talking interactive terminal sessions, secretly capturing screenshots. I mean, they can even take over the mouse and start clicking on Windows machines using a secondary package called @nuttreeforknut.js. They're literally taking the wheel of the developer's computer.
Which raises an incredibly important question about our defense strategies.
Right.
Because the malware doesn't attack the application the developer is building. It actively hunts for the developer's local configurations.
Right.
It scours the machine for editor history from tools like VS Code, Windsurf, or Cursor. It steals configuration files for AWS, Azure, and AI tools like Anthropic Claude. It hunts down SSH keys, cryptocurrency wallets, and browser session data.
It's a complete smash and grab of the developer's most sensitive credentials. It's like trying to rob a bank by first kidnapping the architect who designed the vault and stealing their master keys.
Exactly.
And as Jay Frog, who did the technical write-up for this, pointed out, these plugins are often loaded in CI/CD environments. These environments have the keys to the kingdom: source code, cloud deployment keys, production secrets.
Which is why the practical impact here for you, the listener, is so critical. This highlights the extreme danger facing development pipelines. If any of those spoofed packages were installed in your environment, you must assume total compromise.
You can't just delete the package.
No, absolutely not. You need to rotate all cloud credentials, block the malicious command channels, and critically, you need to enable dependency scanning in your CI/CD pipelines so that newly published, typo-squatted, or suspicious packages are flagged and quarantined before they are ever installed on a developer's machine.
It is a stark reminder that the human element, the tired developer on a Friday afternoon, is often the most targeted link in the chain. So let's do a rapid recap of the 3 clear takeaways from today's deep dive into our digital plumbing.
Sounds good.
First, we saw that human intuition is still unmatched at the very edge of complexity. A human researcher caught a tiny 6-instruction timing window in the bad EPOL kernel bug that an advanced AI simply walked right past because it couldn't conceptualize the race condition.
Right. And second, we saw the exact opposite scenario. A basic $20 AI fuzzer uncovered 7 massive memory flaws in FAT-Fs affecting millions of embedded devices globally that human auditors had completely missed for years. If your infrastructure relies on embedded devices that accept physical storage, you need to lock down your physical ports and heavily audit your upstream dependencies.
And third, we saw state-sponsored actors bypass both human error and AI by socially engineering the developers themselves with fake NPM packages, proving that a flawlessly secure codebase means absolutely nothing if the architect's workstation is compromised from the start.
It's a complex, evolving landscape, and it requires vigilance on multiple fronts. You have to patch your core servers, secure your physical hardware, and ruthlessly verify the software dependencies you bring into your house.
I want to leave you with one final provocative thought to mull over. We talked earlier about bad EPOL and how AI is rapidly changing vulnerability research. Well, an AI security firm called Binario recently used an autonomous AI agent to hunt for flaws, and it successfully found and exploited a remote code execution bug in FreeBSD's NFS server. The designation for that is CVE 2026-4747.
Right.
Here is the kicker. That bug was 17 years old. It had been sitting there completely dormant in the code for nearly 2 decades. If off-the-shelf AI is now capable of digging up 17-year-old ticking time bombs in our legacy code, how many other massive leaks are sitting in our core digital plumbing right now, just waiting for an autonomous agent to wake them up?
A sobering thought, and one that guarantees we will have plenty more to discuss in the very near future.
Absolutely. Thank you for joining us for this deep dive. Keep questioning the code you trust, keep learning, and stay secure. We'll catch you next time.